All right, we're on.
All right, class, I'm sorry I can't be there today. I guess Kevin's probably already talked for 25 minutes. But this is computational model. And going through the computational model, what we've tried to do is help you visualize what's going on. So the one-dimensional portion of this is just the standard probability distribution function. And you've seen that several times with the Gaussian curve in the center. It's the central limit theorem when you're doing Monte Carlo that hasn't been normalized. When we go to two-dimensional, which is the cover of the Smith text and the others, we are going ahead and having two PDFs, and we're cross-plotting, and we're looking at the total density there in the center. Looking at that density in the center, we get a total probability distribution. At the bottom center curve here, where you've got the colors, we can actually omit all of the domain space in white. That saves us a lot of computational time and allows us to stay on there. As we go to 3 dimensions, it's the same thing. Now we're taking this 2-dimensional plot and we're putting it on each of the faces of the cube, and we're generating a 3-dimensional sphere, basically, of influence in the center, which allows us to omit about 60% of the domain, thus saving us time. Remember that this curve has to have real data. The reason we can do this is we have experimental data that lets us narrow it into this region. So that is how we would do it visually for the 1, 2, and 3 dimensions. For our example, we're doing 9-dimensional. 9-dimensional, basically, you can take the blue pill. Kevin should have handed these out, and the story ends. You wake up in your bed, whatever you want to believe tomorrow. You take the red pill, we can stay in Wonderland, and I show you how deep the rabbit hole goes. Now remember, all we're offering is the truth, and there is no spoon. So we take that 9-dimensional Latin hypercube, we cross the probability density functions of each parameter to create a hyperparameter. Then we put that into a Markov chain Monte Carlo. For each of those hyperparameters, which is this cross plot, we have a hypervariance. What we're trying to do is make sure from the 3-dimensional example that you stay in the domain that we have real data on. Unfortunately, doing this approach gives you smooth curves, and we know that field data is very rarely smooth, very rarely ideal. So we need to insert the noise that we would see in the field, which is basically a model of non-ideality. We're going to do that through various different math means. We're going to do wavelet decompositions, which is basically noise signal processing. We're going to use GASPs to make sure that we get the terms right and stay in the distribution. And then the hypervariances and the hyperparameters are going to make sure we stay within that domain. So Kevin made me truncate 7 pages of math down to this one slide because that was all we could get to. The wavelet generations, we're applying a wavelet that is based on the real data, a wavelet based on the bias, and a wavelet based off of the error, which is the difference between the real data and the field measurements. That wavelet, as you see, psi is a function of time. If you ever look at any exponential curve or any decaying model, at time 0, we know what it is and our errors are small. As time increases, that error can propagate. So the intent here is that the wavelets and the wavelet decomposition is to try and minimize that propagation of error as we get further away from time 0. Going back, this figure is the cover of the Smith book. My internet connection is unstable. Okay. Here we have 2 parameters, Q and Y. We're showing the prior distributions of Q and Y. You get a hyperparameter cross plot that is showing you the distribution with the mean down the side. The GASP is making sure that you are staying within your curve and staying within that domain. That's just a standard Gaussian application off of the mean. As you can see, it flares out at both ends the same way that the standard Gaussian does it in 1 dimension. So in 3 dimensions, 9 dimensions, you can see the edges are more fuzzy than the core. And then the hypervariances and the other things that are applied to noise and the mean. The noise is generating the black dots here. The hypervariances and the others keep this in the acceptable domain. It's basically an accept-reject criteria as discussed in the Shaw text. So the computational model, there were two potholes, hot pothole A, pothole B. They did 65 runs. They used different parameters for each pothole and different calibration parameters, but they got through. And what you see is, you see some errors where it's overestimating the dip and it's overestimating the response up here. The curves are tighter as time is closer to zero, and they actually spread out more as time gets longer. So in this case, it was fortunate that the smaller pothole was at the longer time scale. But all in all, it was a fairly good match. After they've done the computer model for vehicle 1, you go back and generate posteriors. So the blue lines represent the priors that were fed in for each of the parameters. U1 and U2 are the calibration parameters. X1 through 7 are the measured parameters. As you can see, it's a normal distribution. It's been normalized, so the scale is 0 to 1 on everything. As after the runs, we come back with posteriors, which are the green bars. It tells us that they got very good estimates, that essentially the Gaussian priors are correct for X1, 2, 3, 4, and 7. Guess for X6, we still see a central limit theorem being applied, but it happens to be skewed to the left, so this would imply that we normalized it wrong, so that the wrong prior was assumed. The distribution is correct, but the normalization was off. This other one, we have a X5. The authors and Kevin and I believe it's a tuning parameter. What you see is it's not a normal distribution, it's not triangular, it's not uniform. It's showing heavily skewed high. So that is a model tuning parameter, or it's a tuning parameter where we don't have the right facet there. It may or may not be an actual phenomenon that dominates. So this generally matches the Monte Carlo and generates the Latin hyperQs response. The reason we got unexpected distributions in 5 and 6 is there were phenomena observed in the model that had not been observed before. So the comparison of the field data and the computational model is pretty close. We're getting within the bias, and we're overestimating the peaks, but that's part of the polynomial fit, and we're not necessarily making the turn at the right moment, but it's within the error that was expected. It's close enough. So the vehicle 1 test data, which this is still the first vehicle, using all of that error, what it's telling you is this is the bias function. The bias is the difference between the real effect and the model. So for the first portion, until we hit that bump hard, we're basically under-predicting, but then we over-predict, and then we have some moments of under-predicting. But all in all, it's fairly close. So the bias function's in the dotted line, then the tolerance bounds for that bias function are shown as the highlight. This is the difference for vehicle 1. Now we take that model and apply it to a different vehicle with different X1s through X7s to get the new portion. So the vehicle 2, in this case, we're predicting what we run the model before the experiment, and we want to see how well they get together. Again, the dip is at 10 seconds. The red represents the field data. So pretty much the only difference here is it's the second vehicle. It's the same potholes. It's the same speed, same normalized time. The computer model is under-predicting in the first dip, and then you're seeing the lines spread out as time has increased on, causing you to not make the correct curve here. The bias correction pretty much stays average between the two. You can see it. And of course, the tolerance bounds get their widest every time there's a curve. But all in all, it was a fairly representative portion. Again, the dip was well under predicted. And that could have to do with that parameter X5 and X6. So the posterior uncertainties, the green bars, they all seem reasonable. They indicate that we can extrapolate. It mostly works. Now, the reason the authors are using this case study, they're saying, okay, this is something we can measure. This is a field thing. We can reproduce it. Vehicle 2 and Vehicle 1 had very similar responses. They're very close to our models. However, how do you extrapolate this to a larger model? Specifically, how do you extrapolate this to climate modeling, global warming? So the warning signs as you go through the extrapolation, the big one is at time 10, there was a phenomenon we had not observed with Vehicle 1. We didn't get the second bounce with Vehicle 1. Since we had not observed that second bounce, the model wasn't tuned to it. The model couldn't predict it. So if there are phenomena that occur that have not been observed before, this is the Bayesian portion, then you can't adapt the model to it. That's a huge error. That's a huge thing. That means long-range forecasting is really off, and that's why you can watch a 10-day weather forecast, and it significantly changes because as they observe things, they change them. The process being studied is extremely trivial compared to climate change. So although it was successful, you can't be a politician and say, oh, well, it was successful, so everything's successful. The unknown input parameters were real tight. The discrepancy function worked, but the uncertainty ranges here are well defined, they're well known, and they're fairly uniform. If you're having prior distributions that are not uniform, you're going to have even more extrapolation with the error, especially as a function of time. And then the key thing here on the validation to complete the VVUQ cycle is we had to do a full posterior analysis in order to get the successful prediction. You can't do a full posterior analysis in climate change problems and large problems like that. You just, A, don't have enough data, or B, don't have enough time. So ending on this topic, the priors versus the posteriors. The priors are what you assumed going in based off expert knowledge and everything else. The posteriors are what you get in the end. If your posteriors don't match your priors, like here with the potholes, then you probably can't extrapolate that model, and it's not useful for significant prediction. If your posteriors match your priors quite well, as they did in this case study, then it's a probably pretty good model. So now, sorry, Kevin, you get all the questions.